Hi, I'm Doyle Bishop with Tulsa Heaters Midstream. On this channel, you can expect to hear about all things related to process heating, but sometimes the topics aren't technical, but most of the time they are, so thanks for joining. Hi, I'm Doyle Bishop with Tulsa Heaters Midstream. Today I want to talk to you about carbon monoxide emissions. So they can be a problem. One is they are regulated in that environmental permits dictate what the emissions level can be of carbon monoxide coming out of a heater. So I'm looking at one of our heaters, which we call show heaters. And what we're looking at here, these are the process coils. This is the pipe that the fluid flows through that we're trying to heat. Obviously behind this is the flame, and it's created by natural gas and combustion air and a burner. So obviously the heat from this flame is heating this coil, and then the coil, the pipe itself is heating the fluid inside. So the temperatures that you see in a typical heater in a flame might be 2200 degrees. Outside of the flame, it gets colder, hence you can see the black, and it may be in the range of 1200 to 1500 degrees outside of the flame. So these flue gases go down, they're heating, and then they make an upward turn. In our heater, they make an upward turn and go through what's called the convection section. So the last bit of heat is extracted from this flue gas in the convection section. Some people call this the economizer. So this is a radiant section, radiant heat, convection section, convection heat. So in the process of burning natural gas is mostly made of methane. And if you look at this, this is what all textbooks would say. H4, which is natural gas, added to oxygen, which is out of the air. Through that is the combustion process, and you would get carbon dioxide, CO2, and water. So you see that magically happens. Well, what they don't tell you is there's a lot of intermediate reactions. In particular, in this process of burning methane, you create CO, or carbon monoxide, and CO is obviously that. It's not quite CO2, so it's partially oxidized. So in the process of doing that, there's CO present in large amounts in the flame. In fact, if I were to take a probe, a high temperature probe, and go in and see what the gases were at this location, there'd be a lot of CO. Well, what happens though is magically, as it goes through the convection section, it exits the stack, there's almost no CO. In fact, a lot of times it's not even detectable levels at a ppm level. So a typical number for regulation for CO, a typical number might be 300 ppmv, and I'll show you what that is. 300 ppmv, that's parts per million by volume. That might be a typical number that heaters are regulated to. However, what we've seen in recent times that environmental agencies are saying, no, that's too high. We want to see something lower. We want 50 ppmv. 50. So obviously that's a lot different than 300. But when things are good and everything is burning right, 50 ppmv is easily achievable. So if you've got a good burner, you've got good air to fuel ratio, your gas tips are clean, you're firing at normal rates, everybody's happy, you're making something less than 50 ppmv of CO. So how is that if I'm maybe 2000 ppm CO here, but coming out of the stack, I'm at less than 50? Well, what happens is this CO continues to burn, it continues to oxidize outside of the flame. So there's reactions, diffusionary type reactions that are going on where my hand is, and even up into the convection section, because CO, it burns, it will oxidize at about 1200 degrees F. So as long as I'm above 1200 degrees F and there's oxygen present, I can continue to burn the CO. But what happens is sometimes heaters are too big. So when we design a heater, someone gives us, hey, we need this much heat. We need 50 million BTUs per hour. So we design that heater for that size. So they put the heater in, and they find out, well, we really don't need 50 million. We're finding out that we only need 15 million. Well, when it's sized for 50, but it's burning 15, guess what? What used to be 1400 degrees where my hand is now 800 degrees. Because there's way more heat transfer surface than I need. So I've got a lot of heat transfer surface pulling this heat out of the flame, so it really cools things down, and what happens is it freezes the CO. So I'm producing 2000 ppm in the flame, but once it gets out of that, it's too cold to burn. So it doesn't burn, it what I call freezes, and hence now out of my stack, I've got 1000 ppm of CO. So what to do? Well, one is you could say, hey, fire the heater harder. But the problem is maybe an end user doesn't need that much heat. So they don't have the option of firing it harder. So one solution that we like to use is, hey, let's come in here. The problem is there's too much heat transfer surface. So you could say, well, why don't you just take some of these tubes out and get this environment here hotter? Well, there's an easier way. I can take ceramic fiber, which is blanket, it's flexible. I can take it and I can wrap this tube. Maybe I don't wrap all of them. Well, I don't wrap all of them. Maybe I wrap 2/3 of them. So maybe wrap these two, leave this one bare, wrap these two, leave this one bare. And so with that, what happens? Well, obviously this cold environment starts to warm up. And so as I eliminate places for the heat to go, this environment heats up, and guess what? The CO burns out. So that allows me to have a heater that's maybe too big to still achieve the emissions requirements that it needs to achieve. And the other thing that happens is maybe 2-3 years down the road, you need the additional capacity in the heater. Well, that's an easy thing. I can climb back in the heater, take the wrapping off of the tubes, and I've got a heater that's right-sized again. Hey, thanks for joining. If you enjoyed this episode, hit like or subscribe to get more information about process heating and Tulsa Heaters Midstream.